I just want to welcome everyone to today's CDHY seminar. I just want to also say that today is the last talk of the season, and we will restart again in the fall. So it's wonderful that Fiorenza is concluding the session for us. I'm very happy to introduce Fiorenza Donato from the University of Torino. The title of today's talk is Electrons, Positrons, and Gamma Ray Halos Around Pulsars. It's a very timely topic. A very brief introduction. Fiorenza is a professor. She's a full professor in theoretical physics at the University of Turin, Torino in Italy. And she's actually on sabbatical now, on leave as scientific associate at CERN in Geneva, which is a wonderful experience. She received her PhD in physics at the University of Torino, was a postdoctoral researcher at Lab Annecy and also at the Max Planck Institute for Physics in Munich as a Humboldt Fellow. She was honored as a 2015 APS, American Physical Society Fellow, Department of Astrophysics, for extensive groundbreaking contributions in astroparticle physics and indirect dark matter searches. Her main research topics are in particle physics and dark matter, cosmic rays in the galaxy, antimatter in space, and physics beyond the standard model. So I'd like to welcome Fiorenza, and just a reminder to everyone that the format of our presentation is 50 minutes plus questions, and then we generally stay on for another 30 minutes, just any general topic of discussion, and it's pretty free-form, open discussions at this point. As a note, we will be recording this for our YouTube archives, so please mute yourself if you're not speaking, and please send us your email if you would like to receive mailings from us directly, and we will add you to our mailing list. So welcome, Fiorenza, and let's get started. Thank you.
Thank you very much, Rashmi, for your very warm introduction. I'm very happy to be here and to share with you some of our results and how the community is about positrons, electrons, and photons around pulsars. So I start sharing my presentation. Good. I just would like to, okay, minimize everything. So even if everybody of you is expert in the topics, I would like to make a short introduction on what I'm talking about. I will talk about leptons, which are one of the species which are measured as cosmic rays, and in particular in this presentation, I will use some vocabulary that distinguishes cosmic rays from being galactic or from being coming from far, let's say, outside the galaxy. What is relevant is that there are direct measurements of cosmic rays that are more or less corresponding to energies about the PV, in which experiments mainly in space measure directly the particle, or other kind of experiments that measure, in particular, this is referred to nuclei, but then I will go into detail with leptons, reconstruct the nuclei by their hadronic showers in the atmosphere. You can see that the E plus E minus flux is less abundant than the proton and the helium-1, which overshoots all, let's say, the greatest number of particles arriving at the Earth. But anyway, they are quite relevant and are measured now above the TV. In the left, in the right panel, there are specific flux measurements for nuclei, just to show that now we have direct data for these particles arriving almost at 10 TeV. The observed electron and positron spectrum is shown in this figure. in which we have collected, AMS has collected, presented the data and collected many other experiments coming from space, from S, which is ground-based, and in the right hand side, one can see the electron spectrum, the total spectrum as a function of energy, in which a kind of cutoff or anyway suppressed flux is observed. So this break is observed at TV. What is the physics that we have to deal with when we discuss, we try to interpret electron data? The propagation equation that I have reported here is, let's say, tuned for leptons, so several other terms that are relevant for nuclei have not been reported here. We can, on a very, let's say, generic way, interpret the flux of E plus E minus, which is this psi unless some factor, in terms of a diffusion in space modeled by a diffusion coefficient D, and a very relevant term, which is the radiative cooling, and in general depends also on time. The diffusion and the energy losses are, let's say, have to be compared with any source of E plus E minus that can be present in the galaxy, which is just the right-hand side of this equation. Very often we solve this equation assuming a stationary state. This is not always true. It depends which kind of physics or sources we are dealing with. Energy losses are for leptons very relevant, most of all for synchrotron radiation on the galactic magnetic field, and for the inverse Compton scattering on all the photon fields in the galaxy. Sources are, I will discuss this in the following, but are mostly believed to be supernova remnants, nuclear fragmentations, this is for electrons, and you will see in a while, which is the main topic of this seminar, also pulsars. The detected E plus E minus differently from nuclei are local or more local because due to their very strong radiative cooling, they lose energy at a very high rate, and they arrive at the Earth only, at the Earth I mean with energies above GeV, only if they are produced within very few kiloparsecs around the Earth. This is visible in this figure in which we have plotted the typical propagation scale length of an electron. We can, for example, take this red line, which is 100 GeV, the source of the electron. So at distance 0, it is here, the electrons, but if it comes from a farther region, its energy will be observed decrease by 1 decade or even more in energy. So this is a main difference with nuclei, or of course with photons even more so, because the portion of the galaxy that we observe with E plus E minus is not that wide. Where is then the end of the cosmic ray spectrum if they lose energies in this very severe way? These authors have argued that whatever the reasons, we can detect electrons up to few TeV or 10 of TeV, but then it becomes very difficult to have a direct measurement of these particles. What about the cosmic ray experiments measuring in general cosmic rays? We have here a situation in which you can see that at the moment we have AMS in space, CALET and DAMPE as well. Other are projects, and then we have small detectors, but they are not measuring leptons specifically. So the energies are covered up to very high numbers, going beyond the TV if a flux is there. This is, I'm going very quickly on this topic, but you see that with increasing with time, our detectors have improved a lot the precision with which cosmic ray data have been and are measuring now in space. This refers to nuclei, and this plot refers to our topic, to electrons and positrons. So also this branch of astroparticle physics, I would say, is now a precision physics case. This is for other nuclei, and this is for ratio, which are very important for calibrating our theoretical models. So this is a precision physics which must be dealt also from a theoretical point of view with the same level of precision if possible. Yeah. A very few words on nuclei, because they are the species on which we tune our propagation models that also are used to compute the E plus E minus fluxes. Here you can see just one example. There are many papers from several groups in the literature that have built very complex models and are able now to reproduce, to predict the AMS data on nuclei, on nuclear ratio, and also isotopes, and even on antimatter to matter, the antiproton case as is here. So the main result that I want to communicate here is that all these pieces can be predicted together. There is a consistent model with several free parameters and uncertainties yet, but which points toward the diffusion coefficient power, which is close to 0.5. This data and the theory models that we have are difficult to interpret because of many free parameters, and among the ingredients, there is a huge number of clock sessions that one has to include, in particular for the production of secondary species, so species produced by spallation, which are still hampering our field to be a precision field. Of course, there are other points, but these points linked to high energy physics at accelerators is now becoming very relevant. And this is just to say that we have dedicated few workshops, the last one a few months ago here at CERN. So there was a real fertile collaboration between astroparticle physicists, experimental physics in cosmic rays at accelerators, with a common objective to try to improve this sector. And we have written altogether a paper which is now submitted to physics report, in which we also provide some indications for the measurements to perform at colliders that as kind of cascade will improve all the field. Let's come now more specifically to the sources of electrons and positrons in the galaxy mainly. First of all, we have a guaranteed source of secondary. Here I put E plus, but similarly, we have E minus. The paper that we produced was emphasizing positrons, but there are results also for electrons. Secondary E plus E minus are produced by this number of reactions. This is the reactions on proton in the cosmic rays over hydrogen in the interstellar medium. This is only one of the main reaction, because we have also helium in the interstellar medium and helium and other nuclei in cosmic rays. So this is just one of the shots that we had to compute. We did let's say a complex analysis of existing high energy physics data to fit the Croc sessions for the production of E plus E minus, and the result is that if we fix the size of the magnetic halo in which cosmic rays propagate and also are confined, so this is a free parameter of the models, of many models that deal with cosmic ray propagation, we have that the uncertainty due to Croc session, let's say, is below 10%. It is not negligible, but this is the size. Electrons can be produced from supernova remnants. Indeed, we believe that they are the main progenitors of electrons, and we believe that they are produced with the same mechanism with which also nuclei from proton to iron are accelerated. Let's say the spectrum with which electrons are accelerated is far from being trivial to be predicted. And in general, one people adopt some, let's say, effective phenomenological expressions, as this one that I have written here, in which the injective spectrum is generically a power law, as one can predict from some, let's say, physics principles, with a cutoff which follows an exponential law with the energy, which we don't know exactly, and is typically a free parameter of the model. It is possible that few supernova remnants can contribute at least to the high energy flux, and that additionally a flux of electrons comes from a smooth supernova remnant distribution. Electrons and positrons, in this case, the production is fully symmetric, can be produced from pulsar-wind nebula that are inhabited indeed by very high magnetic fields. And these magnetic fields can extract a wind of electrons from the pulsar surface, and the plus E minus pairs can be produced in electromagnetic cascades. This is a very efficient, with high multiplicity reaction, let's say, way of producing pairs. And similarly to supernova remnants, these particles can be accelerated to a very high energy with the law, which follows again a power law, even if with different index. These pairs can at some point be released in the interstellar medium, and these E plus E minus pairs, when they are still nearby their sources, they can radiate by inverse Compton scattering and by synchrotron radiation, which is something that I will discuss in a while. The total energy that a pulsar-wind nebula emits in E plus E minus is a fraction of the total spin-down energy. This fraction is typically referred to as the efficiency to produce E plus E minus. In this figure, I just have made a choice to show some recent results. Several groups have reached similar conclusions about the interpretation of the electron and positron fluxes. Here they are separated. This is the reason why there are only AMS data, because AMS, as Pamela in the past can now discriminate between E plus and minus because of magnetic field on board the detector. We see the measurement, the black dots by AMS for the electron case, and the gray dots is for the positron fluxes. The different curves are a model for the production of primary, so directly injecting the galaxy electrons from supernova remnants. This is the blue. Then we have a fully symmetric production from pulsars, which is the red, so equally plus and minus. And then we have the production of the secondary, so produced by spallation, by nuclear reactions, E plus and E minus. So you can see with your eyes directly in this figure the relative magnitude of these different sources. It is also clear here that the data can be explained, I would not say easily, but without the addition of any exotic sources. For example, dark matter has been invoked sometimes to explain the high energy behavior of the positron fraction here. It is the absolute flux, but it's the same reasoning. So a combination of supernova, secondaries, and pulsar with nebula can, in principle, explain the data. A lighter, so not so clearly visible break is present around 42 GeV in the A- spectrum, and it can be easily explained by the interplay between supernova remnant and pulsar with nebula. How is the role of pulsars? I'm now concentrating on the role of pulsars because I want to connect this to the gamma ray and in general to the photons that we are observing towards these sources. In order to understand the role of pulsars, is there some question? I hear. Okay, maybe it was just a spare noise. We have performed a simulation of a population of pulsars. So what you can see in this plot here is a simulation in space of the pulsars distribution and of a simulation also of the pulsars main properties. And so we have a kind of, let's say, fake galaxy in which we have then looked for the contribution of this, let's say, all the single pulsars to the positron flux. And here we have reproduced some exemplary extract section from our simulations. And meaning is the following. You can see here the positron data from AMS. The gray line is the contribution from the secondary E plus, and all these other lines are contributions from single pulsars simulated here. The colors are discriminated between the distance of the sources from our detectors. So the main, I think that there are two messages here. The first one is that the contribution of pulsars is dominant above 100 GeV. Below this energy, secondaries are still relevant. Above 1 TeV, we don't have data, so it's difficult to put any constraints. Anyway, above 1 TeV, we have still secondaries which are present and that will set the minimum level of observation if detectors can one day go above this energy. So secondaries are there. And also the presence of secondaries will forbid somehow a strong evidence for a sharp cutoff because these particles are unavoidable. And the other message that is visible here is that depending on the specific simulated galaxy, we can have one single pulsars that dominate the spectrum or several ones, or even many of them. This is another figure in which we have reproduced other parameters with respect, for example, to the time, to the age of these sources. What is relevant is again that the 1 3 kiloparsec ring is the richest in terms of V+, and of course also the shape of the spiral arms and the propagation length is crucial in determining, or it is relevant in determining, the total final flux. A result of these simulations was that indeed the mean number of pulsars or pulsar with nebula indeed that produce a flux higher than the experimental flux error in at least one energy beam. So the relevant pulsars, this is the meaning, are not that many. So only few sources can explain most of the measured flux. So with these results, we then decided to pick the full pulsar catalog, which is, we know, anyway not complete, to make a more realistic study. This is a slide in which I just put some formula to say that in order to predict the E plus E minus pair emission from pulsars, we have to make some assumptions, and these, let's say, different scenarios can be drawn. We have indeed distinguished a few models for the injection of pulsars in the galaxy, which can be fully described in these papers. So what we have done here is that we have considered all the pulsars present in the ATNF catalog. So we have taken position, age, and the energy loss rate. So this is no longer simulated, and all the other parameters are then simulated within these 4 different injection scenarios. So it is a much more realistic understanding of E plus and also E minus, but produced by these sources in the galaxy. And you can see here just one way in which our results can be understood. Every line here is a real pulsars in the catalog, which is within this interval of distance from us. The secondaries are always there. The blue line is the sum of all the contributed pulsars, and depending on the injection model, we can have very different shapes and intensities from these fluxes. In particular, I would say maybe the most realistic modeling is this so-called tau zero distribution. Just shortly, tau zero is a typical pulsar age, which sets a timeline for the first stages of the star. There was an habit in the literature, and we also did several times, to fix this value of tau zero equal for all the sources in the galaxy, which is, of course, not correct in principle. In this other model, tau zero distribution, we assume that indeed this tau zero can follow some distribution, motivated distribution, let's say. And I believe that this is much more realistic than this model, and this delayed injection is very similar to model B. And the last model, which is called two-zone propagation, is related to what I will show in a while, which is a model in which a diffusion regime is valid in the very few parsecs or tens of parsecs around the pulsars, while outside this zone, it is the average galactic diffusion regime that is fixed. So you can see that different contributions and different scenarios and also different existing or non-existing cutoffs can be present with more realistic data. We have made the exercise to study the, let's say, the role of the most relevant pulsars in the catalog on the total flux of positrons in the galaxy. All these results are constrained by AMS data. And the main message in this figure, in these two plots, is that the top 10 brightest sources in each realization that fit AMS data describe almost 80 or at least 50% of the total E+ observed by AMS. This is the average of the top 10 brightest sources. These are the absolute 10 brightest sources, but the message is not that different. So few sources can explain the high energy E+ data, included, of course, a secondary from inelastic collisions between nuclei and the interstellar medium. As a function of the flux, this is another way to see what I just presented to you. So this is the contribution of the top 10 pulsars to the E+ flux. These are the secondaries with some theoretical uncertainty band. This is the data, and this lighter contribution here and in all the other plots is the contribution of the rest of the pulsars populations. So it depends a lot on the injection that the injection model for the pulsars. So the emission model and parameters are very relevant. Some models are predictive above the TVE, for example, this one and this one. Other ones have uncertainties that cannot give any clear predictions above the TV region. Now, I try to connect the emission of positrons around pulsars from pulsars and the gamma ray halos. So let me first of all go a little bit historically, when a few years ago the collaboration detected the presence of gamma ray halos around Geminga and Monogem. They are very brilliant, and nearby pulsars, the distance is in the, let's say, more or less 250, 300 parsecs from the Earth. This is the figure in which the two, Geminga here and Monogem, are set in the sky, and this is the significance map. While in the panels here at the right, they have plotted the surface brightness as a function of the distance from the pulsar in parsecs. So as it is clearly visible, some photons have been detected not only in the very center of the pulsars, but in a region which extends at least few tens of parsecs from the core of the pulsar. And this is true for both sources. The interpretation that the collaboration proposed and that has been explored by several groups is that very likely these gamma rays have been produced by inverse Compton scattering of any plus and minus populations directly produced in the pulsar. This plot is just to show how it works, or the orders of magnitude that are at stake from a particle physics point of view. So we have electrons here. We compute the Compton, inverse Compton is just because of inverse kinematics, take into account also the correction from field theory, which is the Klein-Shina regime, and we compute the energy of the upscattered photons. So this plot is to show which is on a, let's say, gross basis, the relation between the source of photons, which are these electrons, and the energy of the photon. So this P divided pi max, P max is the power of the inverse Compton. It is very strictly connected to the cross section. So, for example, let's take an electron of 10 to the 4 GeV, so 10 TeV, okay? The highest emission power by inverse Compton is the white wine, the white one, and the photons that are produced by this population of electrons have energies which are more or less a factor of 10, 20, 50 less. So this is the connection between the source energy and the electron energy. The electron and the photons. So Oak, which measures photons, let's say, above the TeV in this grossly in this energy range, is indirectly testing electrons that are of at least 100 or even more TeV. Further analysis of gamma ray data in the Fermilab data, so at a very small, much smaller energies, have been, we have done this analysis, and we have detected a halo in the Geminga, in the direction of the Geminga pulsars, which is can be interpreted in terms of inverse Compton scattering with the model, which is also consistent with the Oak data, which is this region here. We have also analyzed other Fermilab sources, and few of them show extended emission also in the Fermilab data. And for a review on the connection of gamma ray halos and pulsars, I refer to this very complete review by Amato and Recchia. The detection of gamma ray halo has been also performed by LASO in particular. This source here has been measured to have an extension of several degrees from the very center of the source. And in addition to the surface brightness, also a spectrum have been performed, have been measured, which is these 3 points here, and an upper limit at energies of more than 200 TeV. This is, in my opinion, a very interesting result, because not only it measures an extension around another pulsars at very high energies, but it is really the indirect evidence of extremely high energy, plus minus, in this source. Just a short connection coming back to the pulsars, the halos around them, and the effect on the positron flux. So we have done an exercise around for Geminga, for the halo measured around Geminga, and a model in which we can explain the halo around Geminga is translated into a flux of positrons, and you can see that one single source as Geminga can contribute significantly to very high energy positrons as measured by AMS. The interpretation of these photons diffused around a few pulsars that have been measured by now three different experiments, Oak, Lasso, and Fermi, is possible, typically possible, if we put let's say a diffusion which is suppressed in the halo around the pulsars. It is the most of the model that explain the gamma ray data around in the halo around the pulsars make the hypothesis require that the diffusion coefficient around these sources is suppressed by at least 2 orders of magnitude with respect to the average diffusion intensity which is present in the galaxy. These results has been further confirmed by Hawke, which has performed an analysis of the data with more statistics. You see here Monogem and Geminga. And they also have now presented a spectrum for these sources. You can see here the data with some simplistic models for the emission and also the prediction from this band here, which is made according to a template of inverse Compton scattering with the suppressed diffusions, which seems to work quite nicely on these two sources. This improved analysis of the Hawke data has produced a very precise surface brightness as a function again on the distance from the source. The dots are the data, the green is the model with inverse Compton with suppressed diffusion. And you can see that given that these sources are very nearby, at some distance from Geminga, there is an excess which is due to monogem emission and vice versa. So the analysis that they have performed has been a combined analysis because of kind of interference in the photons from these two sources. And again, this combined analysis strongly favors a diffusion coefficient which is suppressed by at least 100 times with respect to the average in the galaxy. We have also proposed some years ago a different interpretation of the halo around pulsars in which in alternative to invoking a suppression of the diffusion coefficient, one can notice that if these particles, I refer to E plus E minus, are very energetic, here the example is for a 10 TeV particle, when they exit the very center of the source for a while, their trajectory is ballistic, so is not yet in a diffusive regime. At some distance from the center, the regime gets diffusive, and there is an intermediate regime which is called quasi-ballistic, which is indeed very difficult to model, which is very relevant for explaining this halo. You can see here, for example, that at very short distances, ballistic and diffusive, I mean, are the same, but then the difference increases with going to very small diffusion coefficients. This is another view of the same, let's say, similar information in which different energies have been clearly separated, and the different curves refer to ballistic, quasi-ballistic, and diffusive regime. So with this complex modeling of, let's say, two extreme regimes, ballistic and diffusive, and an intermediate one, we could explain the surface brightness of Geminga, monogem, and the LASO source. This fit is very good in all cases, and the only, let's say, price, if we have to say this, that we have to pay is that the efficiency that this model requires is pretty high and close to 100%. Anyway, there are several uncertainties in this model, and the option to recover a small efficiency is, I mean, is quite natural. But let's see. I'm just to use my last minutes of the talk to say that in order to better understand the behavior of these sources and the physics that happens around the pulsars and these diffusive halos, one should start to look not only to gamma rays, but also to photons of different wavelengths. For example, if one predicts that there are electrons producing inverse Compton photons, you see here predictions for inverse Compton fluxes. This is a photon flux with different choices for the diffusion coefficient, normalized at some energy, just to make clear the difference. These same electrons, if are in the presence of a magnetic field, should also produce synchrotron radiation. So the same electrons producing these gamma rays should also give photons, let's say, in the X-ray band. This is true for the flux, and this is also true for the surface brightness. So there must be the same kind of physics, the same populations that can, in principle, shine also in X-rays. In this, let's say, seminal paper, we have analyzed, in collaboration with experimentalists, archival data in the direction of Geminga, both for XMM, Newton, and in the NuStar data. We have not detected a synchrotron or anyway an X-ray halo around Geminga, but, this data have forced us to put an upper bound on the magnetic field around the pulsars, which is around 2 microgauss. You see here a multi-wavelength interpretation of Geminga in terms of Oak data, Fermi, and these two X-ray experiments. Very recently, we have also collaborated with the Veritas collaboration, the XMM Newton collaboration, in order to explore the multi-wavelength emission of the LASO source. You can see here the LASO data for the pulsars J0621. Our paper puts upper limits from Veritas data, which are these black ones, and the search in XMM Newton in, let's say, 0.115 keV have provided the first X-ray detection of the pulsars. We don't see, again, a diffusive halo around the pulsars, but with a consistent model that tries to explain the LASO data, the Veritas upper limit, the Fermi-Large upper bounds, and the XMM Newton, so X-ray data, we again are forced or can put an upper bound to the magnetic field, which is about 1 microgauss. So it's not a discovery, but I think it is a strong result. And two sources now, Geminga and LASO J0621, points, let's say, towards similar magnetic field value as upper bounds. So I hope to be in time, and I come to my very generic conclusions, very generic because I think that it is really a very expanding field, so it's difficult to conclude. It is better to make a list of perspectives and wishes for having more data in many bands around several parsers. But anyway, a short summary is that the plus and minus common-ray flux can be understood in a, let me say, quite a natural way in terms of the secondary components and the contributions for supernova remnant and pulsar nebula. Cosmic ray physics is strongly linked to accelerator data. We were a bit ignoring this aspect till a few years ago, but now that we have very precise cosmic ray data, I think that this aspect will be and is very relevant. As for leptons and for positrons in particular, we see that a small number of catalog pulsars can shape all the E plus flux. And the gamma ray halo around pulsars has opened quite suddenly, I would say, a new window on the very complex physics around these sources. I didn't have time to go through, but it is very difficult to try to explain from a theoretical point of view why this diffusion coefficients should be suppressed. There are some works in the literature, but we are very far from a full understanding of these points. And the very message from my side is that only a multi-messenger analysis is to be followed, because we cannot only understand E plus, E minus and local diffusion with cosmic ray data, but really we need cosmic rays, we need photons at very different wavelengths, and let's say beneath we need accelerator data. So I would say which is a multi-messenger and also multi-channel physics that opens in the next years. Thank you for your attention.
Thank you, Fiorenza. Thank you for an excellent summary. We have time for questions. Anyone, please raise your hands. Marco, please go ahead.
Yes, very nice talk. I have a couple of questions. First, you mentioned several times the issue of injection from pulsars to understand what we observe. What do you mean by injections? Can you remind us what are the parameters and what you assume?
Yes. I try to summarize here what we did recently. Injection is in a very, let's say, schematic way written according to this function here that you see, Q, as a function of energy and as a function of time. This is a luminosity function, which is a kind of normalization. And
the screen. Marco, are you seeing a screen? Are you sharing?
Sorry.
No, I'm not
sorry.
using the screen.
Sorry. I was not sharing. So the E plus, E minus per emission from pulsars, we assume that it follows this function here that you see, Q, as a function of the energy and as a function of time, which is the age of the pulsars. The parameters are the index of this, let's say, the power law, the cutoff. This is the luminosity, which is linked to L0 and the age of the pulsars. Another modeling enters in this index, and here, which specifically we assume equal to 3 because it is a breaking index which has this preferred value. This parameter tau 0 can be fixed, or as we did, can be moved in a distribution, some of these parameters can be fixed from catalog measurements, for example, from the measure of the period of P dot and of E dot. So it is a modeling that has several free parameters, and these parameters, here it is the real number of parameters that we have assumed for the source spectrum. There are some other subtleties that are not explained in this plot.
Lorenzo, if you're sharing your screen, we don't see it. Sorry.
Oh, I'm so sorry for that.
Yes, you should share the screen. Yes.
Yes, I'm so sorry. Okay, now it's
Yes,
done.
that's better. Thank you.
Yes, I talked. So sorry, Marco. I talked.
No, but we know what you're talking about. We know what you're talking about.
Yes. So I was referring to this formula here
Yes.
for the QDE. Some free parameters that we choose, some other parameters which are connected, linked to parameters that are measured, in particular that are present in the ATNF catalog and which is dominated by radio observations.
So you're using the actual parameters of the known pulsars, so which are different from pulsar to pulsar, right?
Yes,
Right.
absolutely.
And you said that about 10 are those which dominate the.
We find this. So just to be precise, so all the parameters of the pulsars that are available in the catalog, we use them.
Okay.
Some other parameters are not present in the catalog and are kind of model dependent. And for these parameters that you can see here, we made simulations, okay? The result, yes, is that few pulsars, in particular at high energy, dominate the spectrum, if this was your question.
Right. But is there room for new pulsars which are yet undiscovered?
Yes, absolutely.
Right.
It is possible, and I'm perfectly aware that the catalog is incomplete, and
Right.
we don't know if some other pulsars is maybe blind in radio or in other wavelength, but can still emit some leptons. All these pulsars that I show here have an efficiency of conversions of the energy of the pulsars into E plus E minus pairs, and this efficiency is a free parameter for us. So
okay.
Few parameters can be moved, and in particular, this efficiency, which is about 10%, could be modified by a little bit, hosting new pulsars, yes.
But you should see a dramatic, if there is a large number of unknown pulsars, you should have a large discrepancy between the contributions from these 10 to the actual data, right?
Yes and no, because what you see here in this figure, indeed, is, maybe it was not clear, the result of a fit. So in these results that I'm showing, I only accept pulsars with their set of parameters that do not overshoot AMS data. Of course, some of the parameters, some of the pulsars that, let's say, some of the parameters of catalog pulsars that we have simulated gave wrong fit to AMS, in particular wrong fit because of overshooting the data.
Right. Or maybe even being below the data, so that you have a fit which is too good.
Yes, I mean, you have a fit which is critical in the region, let's say, above 100 GeV up to TeV. In this region, the secondaries cannot explain the data in any way. So yes, one could have some coincidence for which all what we simulate was too low. But it's easy to overshoot.
If I'm allowed just a very quick comment, then I will shut up. I'm a little bit worried about the low magnetic field that you're getting from the synchrotron constraints, because 1 microgauss is really at the limit. Are you worried also, or?
Yeah, I mean, I don't know if worried is the right word, but we are aware that it is a low number. This is the number, to be precise, this is the number of the magnetic field in the halo, of course. It is not high. If the average in the galaxy is 3, it would, in this case, we are saying that it is a bit below the average. I'm not that worried because it is not 0.1, but this is what we find, at least what we find also in this other case of LASO source, in a consistent pictures that try to explain many things from LASO energies to KV energies. These are very first attempts to try to see the halo of pulsars in this way. Maybe we have to refine something, and I don't know what to say to you more than this.
Well, it could be connected with the low diffusion coefficient.
Could be, yes.
Probably it is, yes. Okay.
Yes, which
Thank
is
you.
implemented here anyway. Okay, so
Right.
this implies that this models has low diffusion around the pulsars and high diffusion as well. It can be.
Could be, yeah. Very interesting. Thank you.
Thank you.
Thank you. Felix, go ahead, please.
Just first a comment on this previous discussion about the magnetic field. And well, very last, this claim that diffusion coefficient could have impact on that. It could have, but if you take exactly the same size of gamma ray source and X-ray source, and doesn't have. I mean, you just take the data what you have, so it's irrelevant any diffusion coefficient if you really take exactly the same area. So that is the and I am afraid that really X-ray size and gamma ray size are not always the same. So that is we should take into account. If not the same, of course, then we have to assume some propagation model, and then of course diffusion coefficient could have an impact on that. Now about the magnetic field, one of course is low, not a bit because energy density is factor of 10, but again, here comes the question, it is interstellar medium or pulsar in nebula. So if you are talking about pulsar halos, then it implies interstellar medium. But if it's not the pulsar halo, but pulsar in nebula,
We lost
is different
you.
story.
Sorry, Felix, we lost
because,
Felix,
really?
we lost you. Could you please repeat?
Yeah, just do you hear me now?
It's
you. Now,
better now.
yes.
Oh, okay, sorry. So what I want to say, so I was talking about magnetic field, right? So that was
Yes.
that. So magnetic field could be infinitely small, formally, theoretically, if it's possible in nebula, but not the interstellar medium. So when you're talking, there are two different sources, one the pulsar in nebula, another one pulsar halo. pulsar halo when electron positrons freely propagate interstellar medium. And of course, their magnetic field perhaps should be a bit larger than 1 microgauss. Even maybe one is not dramatically small, but still it's small. But if it's the source is a pulsar wind nebula, then it's completely different situation, because then magnetic field could be really very small. The problem is just when you have explosion, you don't have any remnants from the interstellar medium. It's just pushed out all material, including magnetic field, and the pulsar wind brings its own magnetic field, and depending the size and the power of the pulsar, magnetic field could be small. It could be much smaller than 1 formally. So that is this is my comment on the magnetic field. Now I have my own question about the derivation of the diffusion coefficient from data, for IMS data. And you once mentioned that there's a amazing accuracy for the diffusion coefficient power law index 0.5 plus minus is very small. On the other hand, we know there are anomalies, and maybe I missed that, but I think you didn't mention about anomalies, because we know now certainly there are anomalies like the boron-carbon ratio is quite different than these standard predictions, and that probably hardly could be achieved with standard diffusion coefficient. That should be, there are also anomalies with the antiprotons. What concerns electron positrons, these probably are not the best messengers to get information about diffusion of particles, because, as you said, these guys are coming from nearby pulsars. So that is simply very, very local information. But the secondaries, I mean, good secondaries like boron-carbon ratio, which is very indicative, they tell us that should be very strong anomalies. So we have to revisit this standard. Okay, that is my.
I missed your last words, but I think I have understood what you wanted to say, Felix, and thank you for the comment. Indeed, yes, you're right. There are anomalies in this data. First of all, there is a rising of a hardening of all the spectra that AMS measures at about 300, 350 GV. I don't know what is the anomaly linked to antiproton over proton, but anyway, as far as the data become precise, this simple view of a unique diffusion coefficient, this is the, let's say, the high energy behavior, is a little bit questioned. What is measured, the hardening, is the hardening of the flux. Then, given that all the primaries have been measured having the same hardening, and the secondaries have been measured to have quite a double hardening, this effect is interpreted as an effect due to diffusion. What I wanted to underline here is that data from nuclei are very precise. So the level of precision of this data is why this number is so small, and it is derived mainly by B over C analysis. But yes, then there is the hardening, and there are also.
No, I agree. I agree that this number is, but what I want to say in the standard diffusion model in the interstellar medium, you perhaps cannot explain, but this with this 0.5, just fixed one everywhere, you probably cannot explain at least boron to carbon ratio, because
I think that these
needs,
authors explained the data with this number, but nevertheless, I agree with you.
they don't explain very well, I guess. I just simply try to.
Okay, okay. They explain the way you. Sorry, I'm losing you, but anyway, I agree with you that we need refined and more complex problems because several anomalies are there.
No, this is, I think, the
Sorry, I don't know if
big.
Can you hear me?
I think there is a
can hear
lag.
He's breaking up also yep.
Felix, you're breaking up, and I
Yeah,
think
your
there is a
connection's.
lag. Yeah.
Okay, then I
So
stop. I mean,
yeah,
that's not.
maybe.
Then I stop.
Thank you very much for your observations. Yeah.
Are there any other questions? Oleg, please.
Thank you for the very nice talk, Ferenc. My question is like about one thing that I noticed when you were showing calculations based on mock galaxy, maybe that you simulate. So you said that the largest contribution to the positron flux, it seems, it comes from pulsars in the range of distances between 1 to 3 kiloparsec from Earth, from Sun.
Yes.
Is naively one might expect that the largest contribution would come from the nearest pulsars. So could you just maybe explain why is that? Does it apply to the real case of our galaxy where you take pulsars from ATNF catalog? Does it depend on the model assumptions like slow diffusion or whatever you assume about pulsars? Thank you.
Yes, thank you for this comment. And this was, now I try to share, not as before. You are referring probably to this result here,
It
in
disappeared,
which
Firenze. We saw it for a second, and then can you reshare?
Okay,
please?
I try. Yes.
Yes,
that's
what I am referring to. Yes.
Can you see now?
It disappeared again. It appeared.
Okay, so I don't know why it doesn't like the view mode, so I can let it as it is with the frame. Okay. Anyway, it's better than nothing.
Yeah,
So yes, so this is the simulation, and indeed, when we saw these results, we were asking ourselves the same question that you are saying. So there are pulsars very close to us. This is again the effect of age and the effect of distance. But what is relevant, in my opinion, is that in the catalog, pulsars have a name and have a distance. So I didn't want to get the talk too heavy, but probably this is the answer to your question. So the brightest pulsars, in terms of E plus E minus, of course, not of photons, are these ones that you see in this table. And there are surely monogam and geminga, which are very close, more or less 0.2, and other pulsars that are a bit farther, but not even at 3 kiloparsecs from us. And the relevance, the mutual relevance of these sources changes a bit, not always, but changes a bit by changing the injection modeling. I don't know if this is the answer, but
So your mock galaxy just basically maybe has different distribution of pulsars because you don't take them from ATNF there when you know.
The Mach galaxy is Mach, but in some sense it is complete in the virtual, in the simulation. So all the parameters in our Mach galaxy that we could take from data, we took them, but as average properties of pulsars, not as properties of a single source. In our Mach galaxy, we model spiral arcs. When we take pulsars from catalogs, they are what they are. So these are the main differences.
Okay, and when you take them from catalog, the positron flux is actually dominated by the nearest pulsars, like Giminga.
Yes, by
1060.
these ones.
Okay,
Yes.
okay. All right, thank you very much.
Yes.
Good.
But connected also to what Marco was observing, there could be other pulsars not in the galaxy, sorry, not in the catalog, but in the nearby galaxy that shine, and that in some sense were considered as sources in the Mach galaxy. So we have a beautiful simulation, but not fully true.
Thank you.
And the catalog, yeah.
Thank you. Paolo, please go ahead.
Yeah, thanks for the great talk. I was wondering a little bit what Oleg was saying, the galaxy model, there are super bubbles and supernova explosions. We live in a cavity, sort of, and your closest pulsar on your sheet is 0.1 kiloparsecs, roughly. So there's lots of galactic structure, and I'm sure the magnetic field is not homogeneous. So is that an uncertainty in the actual results you're fitting because the diffusion coefficient could be varying on sub-kiloparsec scales? So even though your galaxy Mach is great, reality could be more complicated and therefore.
Yes, you are completely right. It's not an uncertainty because we didn't get into this level of precision. Yeah. Okay, so we didn't include any bubbles or even the local bubble.
Yeah.
This should be done, and this is something that we have in mind for the future. And it can be seen at the different levels. We made a seminal exercise in the direction that you say, not for pulsars, but for supernova remnants. So we built a model which is very simply sketched here, in which we put on demand or not a hole around us, around the solar system, in which we said, you can probably see this green.
Yep.
Okay, so green is more or less the disk of the galaxy in which there is a smooth source population of supernovae, and the hole around us is first emptied and then filled with 1, 2, or the few supernovae this time that we can find in the catalog. And there is a little bit of differences in treating the galaxy as a unique smooth distribution or in this very simplistic, let me say, way. But anyway, I don't think that there is much more in the literature. I fully agree with you. There is a lot to do in this geometrical modeling and also on the diffusion properties. And I just add one further observation that in these bubbles there are no spallations as well.
Yeah. Thanks. Yeah.
It is.
May I just comment? Do you hear me, by the way?
Now, yes.
Okay, let me just comment on that. I mean, it's electrons, positrons, very fragile. And if you want to, you have to find a way to avoid dramatic energy losses in these bubbles. There's a very high radiation losses, and the magnetic field there certainly could be much higher. So, and then for that reason, they could lose energy, at least as long as we are talking about the
Yes.
TeV electrons, 100 GeV electrons. So you need some more neutral environment, like the isolated pulsars with low magnetic field in the pulsar nebula. And we have also, in addition, what you say should be nearby, So is it just this three conditions should be somehow satisfied. Otherwise, in these stellar clusters or star-forming regions, they certainly are produced, but you need still organize the escape from there.
Thank you for your comment, Felix.
I think we are coming to a close. Any other questions? Paolo, your hand is still up.
Okay, yeah, I put it back up. If no one else has a question, I was wondering, we may, with COSY, we may get another 511 kV instrument. So is annihilation radiation interesting? And particularly if you look towards the galactic center, people postulate some large number of pulsars, which are creating positrons, which annihilate. So by looking for the annihilation radiation, will that be interesting? Not for the local cosmic positron flux near Earth, but
Yes.
or in galaxy and galactic models and things like that. Is that
Okay. Thank
is
you.
that a useful direction to go?
To use this data, you mean?
Yeah, yeah. Or if we try and get better MEV 511 kV instruments and improve our sensitivity and precision.
Yes, but COSY will not point sources.
No, it has a very bad angular resolution, like half the.
So it would be more, well, maybe it could help because if COSY will measure the diffuse emission, we can somehow trace back the properties of E plus, E minus in that portion of the galaxy. I would say that it can help not on a single source basis, but yes.
Sorry, may I intervene again? Because Paolo, I mean, if you are GV electrons hardly could contribute to annihilation line because imagine what is the energies. Maybe
So they have to cool. I mean,
yeah. No, you cool, but then you get from one GV electron, you get just called so you waste all energy. So basically, if they are coming non-thermal electrons, energy should be relatively low, like 1 MeV, 100, 10 MeV, maybe even 100. No, I think even 100. You imagine, I mean, just 1% of energy you get in the line from the 100 MeV electrons. So they so basically, if you see annihilation line and you think there are no thermal electrons, cool down, but this should be relatively low energy electrons, something like 110 MeV or less.
But Paolo, we are very worried about the fate of COSY now.
Yes, that's true.
No, but this COSY can do something else. I mean, it's not. It's 10 MeV science. It's beautiful science. But I just want to say, GV electrons is just a luxury, you know, to have a 1 GV electron and to get 1 positron to annihilate. It's just, but
right.
No, but
different.
Yeah, I was thinking more about constraints on number of positrons, because there's a large annihilation flux in the galactic center, and you can get positrons from radioactive decay also in elements in supernovas. So
well, there's a nice constraints, of course, will be, but as I say, there's 10 MeV and less.
Yeah. For the physics of the galactic center, it would be great also for studying this excess that we see in the Fermilab data, of course. If it were dark matter, that would be nice to see the counterpart, these energies, the COSY energies. It's another physics, but yes, let's hope.
Let's hope.
Okay.
Yeah. Well, I think we should stop now. It's 25 minutes past the hour. So let me thank Fiorenza again. That was really an excellent summary. Please send us your slides so that
thank you.
And I also want to thank everyone for joining us for this season. As I mentioned earlier, this is the last talk that we have for this semester, and we'll start again in the fall. Thank you. Thanks for joining.
Yeah,
Bye-bye.
thank you
very much. Bye.
Thank you. Bye-bye.
Thank you.
Bye.